So we will start. So yesterday we have seen that basically three approaches are there to solve any problem, any engineering problem. The first one is the analytical one, experimental one, and the numerical one. So we have seen that while for the simplistic case like the bending actuator, analytical one is the very accurate technique because it will give you an exact solution. Once you are able to formulate the equation, you can play with the different parameters. For example, in case of DMS, frame bending stiffness, restretch of the membrane, applied voltage, and if you are incorporating anisotropy parameter, viscoelasticity parameter, eta, okay. So that follows basically from the simple development of a governing equation. By using the initial condition, we can, after the development of this analytical model, we can evaluate the exact solution. So if you make the comparison with of the analytical with the experimental, it will give a very good result, very good match. So you will get a very good corroboration between the two. Some source of discrepancy again will be there. I am not saying that the analytical one is the wrong one. The reason is while you are fabricating experimentally, we have already seen that there is a chance of lot of error will creep in. Lot of activities we are doing manually. So to overcome that, experimentally people have now using different modified techniques. One of the techniques is instead of a hand layup of the carbon grease, people are using spray up techniques. So in that case you are having a uniform basically the distribution of that carbon grease across the active area, and that will give you more accurate and desirable results. Okay. Now we have already seen that in analytical one, or if you are talking about specifically the DMS we have considered simple homogeneous deformation. But in actual practice, when this type of actuators are used in practical application, they undergo inhomogeneous deformation. I hope all of you have understood homogeneous and inhomogeneous. Okay. So what is happening in the inhomogeneous deformation? If you want to incorporate that, you cannot do that thing in the analytical formulation. It's very complicated. It makes the equation very complicated, and it cannot be solved easily by using the analytical method that we have considered. Okay. But in the finite element method, there is an option, and it is a numerical technique. So you can incorporate the inhomogeneous deformation. So in inhomogeneous deformation, basically your tangent modulus will come into picture. So your modulus is going to vary throughout the active area of the membrane that we are considering. So FEM provide a suitable tool, or we can say that it is a platform by which we can incorporate inhomogeneous deformation. That is one advantage. Second, I have already told you, if you are having a complicated shape. So if the dragonfly we are basically going to fabricate, okay, experimentally, and we want to validate. So analytical it's very difficult, very complicated shape, geometrical parameter, a lot of parameter will creep in, okay, and you cannot take into account all effect of all the thing in an analytical model. So FEM second advantage is that if you are having a complicated shape, it can be a useful tool to incorporate the effect of different parameters. You are getting my point? So each technique has its own advantage and disadvantage. Experimental one is the best one because ultimately you have to implement that. Okay, but sometimes it becomes very difficult to fabricate every time to do experiments. Okay, so I am just telling you a very interesting thing. Nowadays there is a AI based techniques called artificial neural network. I am going to show you that thing also. Experimentally very difficult to fabricate, okay. Analytical very difficult to solve complex equation. You are getting my point? FEM is also a tedious process. If you are having a complex geometry, you need to mesh the element. You have to select the element to mesh the entire geometry of the equipment that you are devising basically. So it will also computationally become very expensive sometime to solve the equation by using FEM. So what the people are doing, for example, if they conduct certain experiment, okay, take some data, do some simulation, okay, finite element, shake some data, and it's like they train. And instead of carrying out all this thing again and again, they will, by using the trained model, they can predict for different parameters. I'm going to today show that thing, how basically people are using this technique. So before going into that, I'm telling you nowadays, I've already told you this thing, three fields are very trending. So if you want to upgrade yourself, and if you are aligned with any one of these fields, you are basically now updated up to the time. First one is soft robotics. I'm not saying because I'm working in that domain, but it is nowadays a very trending. The reason I've already told, it has a lot of advantages. Okay. Second is additive manufacturing. Because with the help of additive manufacturing, you can basically combine different properties, okay, in a single component, and it can be used for very advanced application. Third one is, as you all know, that very trending, AI, artificial intelligence. So please keep yourself updated. It's not like that you are a mechanical engineer. Here also at IIT Indore, our entire course structure get now reformulated as per NEP, National Education Policy. So we are trying to incorporate this trending fields, AI, artificial intelligence. We have incorporated many subjects, okay, additive manufacturing and soft robotics, smart material basically. So without wasting time, let's come to our third important technique that we have to cover yesterday, but we will start today with that. So we have seen analytical, experimental, okay. Now numerical technique in Abacus. So basically there are different software. I'm telling you, you can use any one of these. The main, if you see the process of the development of finite element will remain the same. Initially in finite element software, what you do, initially you develop the geometry. That is one thing. For example, if you want to manufacture this DMS based actuator, you have to develop the geometry of the frame, membrane, you have to define. Or the other thing is, in some software, you can basically, you develop in like SolidWorks, you can directly import the geometry. Sometimes the complicated geometry is very difficult to made in the Abacus software. So you can easily made in the SolidWorks, AutoCAD, you have already familiar with that thing. So there is an option, you can import that geometry directly to finite element software. So that first step is very much clear, I think. Okay. Second thing is, after defining the geometry, what is the important thing? Material. You have to define the material properties of the individual component. For example, we are having dielectric elastomer membrane, frame, stiffener. So in Abacus, there are like different properties are available. For example, if you are considering membrane to be hyperelastic. So in the Abacus or in finite element software, there is a property that you can assign hyperelastic material property to the particular component. In that, it will again ask you which model you want to implement. Neo-Hawkian, Ogden, Mooney-Rivlin, that we have seen. So for example, if we give a component that material property by defining certain strain energy density function by using constitutive models that are available. Second step is clear. So after defining all this thing, third thing is, I am giving a crude way of the step that we are implementing in finite element, okay. So third thing is, after defining the material properties, what you have to do, you have to assemble them, okay. So this step are common, whether you are following ANSYS, COMSOL, Abacus, any software, okay. Then what you have to do, you have to assemble the components to form the final assembly. So in our case, the components are stiffener, frame, membrane. So in Abacus software, there is a tie option. For example, if you are combining a membrane with the frame, so you provide a tie option at the front top surface of the frame, say, and at the bottom surface of the membrane. Frame and membrane, either one of you make the top and the bottom, that is going to club together, okay. And your frame is hollow. So you define the geometry that it is hollow at the center portion or at a certain location, okay. In the tie constraint, what you give, one surface has to be master surface and the other surface to be a slave surface. So it's very simple, you select one of as a master and one of them as a slave. So it doesn't depend which one you are taking as a master and the slave. It's basically required to basically take initial surface as a master surface and the other one which is combining with it is called as a slave surface. So when you do that, it will glue that component, okay. Then you put the stiffener over the surface of the frame by tie constraint again. So ultimately your assembly will be developed. Then the fourth step you can see, you have to give the boundary condition. For example, membrane is initially pre-stretched, okay. So that is the basically considered as either you can give it as an initial condition or you can define as a boundary condition by giving some displacement to the membrane. And you have to fix the component. For example, if you want to develop bending actuator, so this basically the edge is going to be fixed. So you are defining the boundary condition to the clamped edges at this location and pre-stretched to the membrane. You're getting my point? So the next step is post-processing. So before going to the post-processing, you have to define what are the parameters you need to evaluate. For example, if you are conducting a simulation, what we need to get? We need to get deformation, we need to get the stresses, we need to get the strain. So these are the things we want to obtain as an output. So before going to the post-processing, you have to define that these are the parameters we need to evaluate after the simulation being carried out. So that you define. So in the last step, the result you have obtained, that will give you the value of stress, deformation, strain, whatever you want. So the stress can be in 3 direction, okay. It can be the displacement in the or deformation in the 3 direction if you want. So you can define. This is a very basic steps you have to follow in any of the finite element software. I hope you are getting. Okay. Similar step what we have done, we have followed in Abacus software. Okay. But there is one clinch here, as he is asking. There is no direct electromechanical coupling in the Abacus software. So electromechanical coupling means we are already known that when we apply the potential difference, ultimately what we are doing, we are providing the electrostatic force of attraction. That will compress the membrane in the thickness direction and expand in the areal direction. So what is happening? In order to define that, in Abacus we have developed user-defined element. I will show that thing. But I will tell you very interesting thing. COMSOL is a multi-physics software that is available now, in which you are having a direct electromechanical coupling. After understanding the basic algorithm that is going on behind, you can directly select the mesh element, which will give you the result directly. So it makes your life little easier. But I am telling you, it's not like that you go and just implement that element and find out the results. So always try to understand what is going behind it. Algorithm, understanding of physics is very, very important. That physics will remain the same. If you are talking about dielectric elastomer or any type of soft active material, the physics that we are basically discussing will remain the same. Okay. So, okay. This is the basic that I have discussed. How we have started the basically finite element simulation of DMS actuator. Then I will take to the advanced application, dragonfly and this basically flapping and gripper that we have seen experimentally and analytically we have extended that. Okay. So you see, when you select, first of all you define the geometry. This is a frame, the geometry is being defined. This is the membrane. So when it is showing green, it means the property is already assigned to them. If it is like initially we have selected them, it will be like a gray color, like this simple color. Then what is happening? When we assign the material property, it will look like this in Abacus software. So it is a symbol that these are the component with already the material property assigned to them. So this is a frame. So what is the property? We have assigned the polyethylene terephthalate properties, Young's modulus, and all the property to this material. Okay, that I will share with you. Second is dielectric membrane we are considering. So initially we are considering it as a hyperelastic. Okay, so we supply the shear modulus. So in a hyperelastic, basically C1 we have to define. C1 is nothing. It is C1 I1 minus 3. So C1 is mu by 2 shear modulus. So we give the property of this C1. We know the shear modulus of the dielectric membrane. So we put the value of C1 there. Then we are having a stiffener. It is made up of polylactic acid material, PLA material, that we have shown you yesterday. So we give input as a property of this PLA material. Then this is a stiffening frame. It is also made up of this PET material. It is going to basically attach at this location so that it will provide initial stiffening to that and allow it to not bend. So the other direction it will bend, in this location it will not going to bend. Okay. This is the second step that I have told you, assembly. So after assembly, the structure will look like this. So you can see this is the assembled way and this is the coordinate system. The general coordinate system we are following, x1, x2, x3 or 1, 2, 3 direction. So after assembling all this component, it will look like this. So this is the basic geometrical dimension we are considering. It's not limited to you. We can have the variation. Initial start, we have considered some dimension. Okay. Then we have optimized. I have already shown you that we have then taking a finger of this type of shape, diverging. Okay. The reason is we have taken the motivation from the starfish. But initially we start with a rectangular one. Okay. So to basically get the understanding that how we are able to incorporate this geometry in the Abacus software. Okay. Any doubt till now? So the important step is how to give pre-stress to the membrane. This is again a very important task. So there are two different ways in Abacus. So what is happening after assembly, if you give the pre-stress to the membrane that I have discussed with you, so it will going to basically what is happening, the membrane is now clubbed with the frame and the stiffener is already being attached. So now then you are trying to give pre-stress only to the membrane. It is not going to effectively get implemented on that. So you can think like that, already a one structure. So what we are doing, experimentally also we are giving pre-stress separately. Then assembling is being done. So similarly software also will feel like this. If you after assembly you are trying to give pre-stress, it will distort the geometry of the entire assembly. When you release it, it will definitely in the result part it will distort. So what are the basic things that we have to do? We have initially carried out 3 different simulations. In first simulation we have considered a very simple square membrane, okay? And in that square membrane, we are trying to have its initial dimension, okay? So you can consider this membrane like this. Instead of this, we are having a square membrane, okay? So what we are going to do, there is one simulation we have carried out in which we give for example, the initial dimension is 10 mm, 10 mm, okay, square one. And it is of 1 mm thickness. So what we are doing, we are giving the displacement in x and y direction. We are saying that it will get displaced by 5 times in x direction, 2.5 if you are giving biaxially in both the direction. So what we are doing, basically we are trying to give the pre-stretch of 1.5. You are getting my point? We are trying to change the dimension from 10 to 15. How we can do that? Basically we have to give, you see initially this is your membrane, and when you give the displacement, so it's an example, it's 1.25 we have started with, 1.25 pre-stretch. So we have given 0.125 here and 1.125 in this direction and 0.125 here and 0.125 here. So ultimately what you are giving biaxial, you are giving the displacement that will be ultimately serve as a pre-stretching for the membrane. So now after in the separate simulation that you are carrying out, so you says that after implementing the displacement condition, give me the stresses that is developed in the membrane. So after this is basically the simulated view. Initial, final it look like this. And corresponding to that, we know that we are giving the displacement of 0.125. Okay. So we can say that we know the value of stretch that we are giving x direction and in the y direction. That is one thing. So corresponding to that, we obtain what? We obtain the value of sigma 11, sigma 22, sigma 33. So one simulation we carried out, we give displacement, we define the geometry of the membrane, material to the membrane, give the displacement, find out the result. And in the result, we obtain the principal stresses. Okay. So this principal stress we have, for example, for different stretch value. So this stretch value, how we obtain? By giving the displacement. So we are having the value of lambda x, lambda y, okay. And corresponding to that, we carried out different simulation. We make a table. We obtain the value of sigma 1, sigma 2, sigma 3 for all the different pre-stretch value. Now what we are going to do in the second step, second simulation, separate simulation, we go back here. So sorry for the interruption. I hope to the online audience, am I audible and my screen is visible? Just confirm please.
Yes, sir.
Okay. So what I am telling this thing that in the abacus initially or in experimentally, first we have to stretch the membrane, then assemble the frame and the other component to it. Okay. Similarly in abacus, first step is we stretch the membrane in one of the simulation, and in a result output we obtain the stresses sigma 1, sigma 2, sigma 3. Now what you can do, just go back to the second simulation part. So there are 3 simulations: pre-stretch of the membrane, second one is basically the assembling one, and you are trying to obtain the equilibrium configuration, because second stage no potential differences apply. Okay. So in this membrane, basically you are having a membrane, material is defined, provide initial condition as this principal stresses. For example, if I am providing the pre-stretch of 2, biaxial pre-stretch of 2 in both the direction, so what I can do, I can basically find this table separately and provide this stresses as an initial condition. So in an abacus there is an option of providing initial condition. So we provide this membrane, the entire membrane, the initial condition of sigma 11, sigma 22 and sigma 3. So what we are doing ultimately, we are giving the membrane. So what is happening when pre-stretch is provided to the membrane, strain energy will be developed, ultimately the stresses will be developed. So we are already giving that stresses to the membrane in the initial stage. That is actually there, na? Membrane is pre-stretched, then you attach the frame. Experimentally you also do the same thing. So this membrane, in the separate simulation we find the principal stresses, okay, and in the second simulation provide this entire membrane, this principal stresses as an initial condition. Then do the assembling. So when you do the assembling, then repeat the same step. Now in the output you says I want the stresses, deformation, everything, strain that you want, you can get. So what is happening? The initial condition of the stresses will behave like a pre-stretch to the membrane, and when you release it, it will deform your entire configuration to the required bending configuration. You're getting my point? So you see how smartly we have done. We follow the same methodology that we have done experimentally. Okay. So after doing that thing, for example, if we have already discussed, there is a one limitation when stiffener is not implementing a significant. So same methodology we have implemented here. So we have obtained the warping. You can see a clear warping is observed. Experimentally, I have also shown you yesterday, the warping is there. So by putting stiffener, so our simulation software tool also provide a right result that warping is completely elevated when we put the stiffener. That we obtain also experimentally, same thing. When we implement the stiffener, the warping get reduced. Now you see, if you see, look carefully the mesh element. So always you have to judiciously select the mesh. It's not like that you give a number of element to 10,000, 20,000 randomly, no. So for that you have to carry out a mesh convergence analysis. It is also called a sensitivity analysis, okay, or convergence analysis. So in that thing, for example, if you are measuring a displacement in one particular direction, say in this direction you want to measure how much this component or your actuator get deformed. So what you do, you always select a suitable number of element initially as a guess, say 5,000. So in the abacus, when you select the number of element to be 5,000, and there are different mesh element, M3, D4, 4-noded brick element, 4-noded element, 8-noded brick element, triangular element, circular element. I'm not going into detail to that. You have to judiciously select. For example, in the square and the rectangular geometry, always try to fit 8-noded brick element, 4-noded element. If you are having a circular geometry, try to fit triangular mesh element there. Why? Because you see it entirely cover the area of that geometry. So judiciously we have selected that it is a rectangular surface. So we select the M3D4 element in abacus. Now that element, number of element it will ask. For example, if you give 5,000 for an initial start, you obtain a result. So what is happening? You are getting a displacement, say in third direction, you are measuring in along the thickness direction. So you are getting some displacement. Note down that value. Then you increase the number of element to 6,000, 7,000. Again your displacement, you see it's going to change. Whatever you are obtaining earlier, it's going to either increase or decrease. Okay, that is one way. So after developing certain number of the element, you start seeing that your curve, for example, if it is increasing, the displacement here and number of element, you are keeping increasing number of element, either your displacement decreases or increases. It will follow one of the trend. So after a certain number of element, whatever the increase you are giving in number of element, your result for the displacement or stress, whatever you are measuring, will remain the same. So the curve will increase, then it will take a constant value. So at the point where after which increasing the number of element, you are getting the same displacement, select that number of element for all the entire simulation. So this analysis is called as mesh convergence analysis. You are getting my point? So once you have to follow this activity, the reason is you need not to do again and again. So if you say, if you are selecting the number of element randomly in every simulation, always you get the different result and you will never get the accurate and right result. So mesh convergence analysis, sensitivity analysis, very, very important. Whenever you go, if you perform finite element, the first question is that, have you performed convergence analysis? If at that time you say no, your entire results are vague. It's of no use. So always first perform the mesh convergence analysis. So you see the number of element that you can see. If you can clearly look at this, it's very fine. So we have done the mesh convergence analysis, obtained the suitable number of elements required for this, and then implement in the required entire simulation. So that is clear to you. So that is one thing. So you can see in the finite element, after obtaining the results, we are having this type of view. There are two different ways. Experimentally what we have done, we have obtained by using image processing technique, the angle. So here there are two different tools are available. I can give you a glimpse that in one of my paper we have used the online protector for measuring the angle. So you just take the accurate view, isometric view or the required view, take the online protector, put it there, it will give an exact value of the measurement of the angle. Experimentally it's difficult to measure by using online protector. The reason is, when you have seen that your gripper is also something, it will be like actuator is also moving from the bottom side something. So we develop image processing technique to find theta 1 and theta 2 to get the accurate answer. But here in finite element, you can take an image, use an online protector to find the angle. You're getting my point? So you see, we step by step keep on evolving. We provide pre-stretch separately, then we keep it as an initial condition in the second simulation, obtain the initial equilibrium configuration where no voltage is applied. Now the third part is very, very important. Okay. So this is the one of the pictures you can like to see. For different pre-states, we are basically this is initial configuration, and we are keep on evolving. As we keep on increasing the pre-states, what is happening? Membrane is going to provide more strain energy will be developed in the membrane. It will try to bend the structure more, and more initial equilibrium angle you are going to get. That's we are expecting in experimentally also. In the analytical, we have also developed this thing. Pre-stage increases means strain energy increasing, more bending of the structure, more initial angle. So that the results you can see from here. Now the third step, very, very critical, very important and very tedious. First two steps is very simple to perform in abacus. In the third step, basically you have to apply in the deformed configuration upon the active area of the membrane, you have to apply the potential difference. You are getting my point? So in order to apply the potential difference, you need to have some electromechanical coupling element. You are getting my point? So in abacus it is not available. So in order to do that thing, you have to define your user defined element. So this is one of the user defined element that we have developed. I will share the code with you. It's very important for you. You can go through that. So in defining that user defined element, we have make a 8 noded continuous brick element. So you can see that it is a 8 noded brick element. Each node we are having a 4 degree of freedom, 3 mechanical, 1 electrical. That is basically missing in abacus. So you have to define your user defined element that have the degree of freedom, mechanical as well as electrical is being required. Okay. So what is the physics behind it? Already Dr. Prashant Saxena has discussed this in detail. We are having a reference configuration. We are having a current configuration or deformed configuration. Okay. We have to define the strain energy first. So the strain energy is definitely going to be a function of Wright-Cauchy deformation tensors, shear modulus, okay, and the electrical part. This is for the membrane. Then we are having the stress, okay. Then we are having for the electric field expression. So this is basically your entire couple problem in mechanical domain. This we are seeing from the first day. He is explaining balance law, okay. So this is the traction boundary condition. This is the prescribed displacement. So this all are the basic equation that is required for the finite element simulation of the dielectric elastomagnet. So these are all in mechanical domain, and this basically the equations are for the electrical domain. Okay. Then finite element, if anyone of you have done the finite element, what we are basically process we are following, we have to define the residuals. Okay. So in order to define the residuals, we have to consider shape function. So finite element shape function is very, very important. It shows the variation of, it shows what is the shape function. Have you know this thing? Shape function क्या होता है? I am expecting वेरिएशन डिफाइन करता है किसका? वेरिएबल का, मतलब जो तुमको कैलकुलेट करना है जैसे डिस्प्लेसमेंट. So it is basically shape function are the entities that is going to describe you or give you the variation of the quantities that is being required, like displacement. So the variation of u it will give. So by incorporating the shape function along with this, you will get the residuals of the residuals in the basically electrical domain and mechanical domain. So after using this residual, you can calculate the stiffness matrices. So stiffness matrices you can calculate. So ultimately your finite element simulation is going to incorporate Ku equal to F, that basic approach. Okay. So it's a tedious process. I have my one of paper on this. Step by step you understand how we are implementing this basic algorithm or basic formulation. This always remains same. It is not going to change. Okay. So after the development of initial single 8 noded brick element, what we are doing, we already know that there is a relationship analytically between the applied potential difference and the developed stretch. So how we get that? So for example, if we are considering the basic equations, incompressible equations, incompressibility constraint, and we are saying that we are applying this much of potential difference, this much of stretch will be developed. Already lot of people have done the development of analytical model for that. It's a very simple thing. If you are having a single cuboid, we are applying the potential difference. How much the stretch? So here lambda is basically lambda 1 equal to lambda 2 equal to lambda. How much the stretch in the aerial direction or how much the stretch in the thickness direction? Lambda 3. It is 1 upon lambda square will be developed. So analytically, a lot of people have developed this. So what we have done, we make the comparison of our finite single element with this analytical expression. So what you can see, when we keep on increasing the voltage, so you can see their lateral stretches keep on increasing, and this condition we have already discussed, it is called as instability condition. Yesterday Dr. Prashant Saxena has explained that at the instability condition, your matrices that you are using Ku equal to become ill conditioned. Why? Because the order, so some of the element is of order 10 to the power 6, some is of order 10 to the power minus 9. You have seen that? So it become ill conditioned and not able to solve that thing. So the same problem we are facing after a particular level of applied electric potential difference, that matrices equation become ill conditioned and cannot predict the result. But up to this normalized potential difference, it can accurately predict the result. So in order to overcome that issues, yesterday what he has said, there are a lot of method have been developed, J bar method, F bar method, lot of method has been developed. I'm not going into detail to that, otherwise it will be a separate topic to discussion. So for example, if our model predict up to this electric voltage, it is very high voltage also. So when we apply this in our model, finite element, for a particular level of stretch, particular frame bending stiffness, you will get this result, finite element result. You put it with the help of online projector, measure the angle and make the comparison with the experimental one. So already we have the experimental technique developed, image processing for measure the angle. Finite element, we develop a single element, okay. Then on the deformed configuration, on this particular active areas, you define all the single element that is, you have developed, you define multiple element. So have the mesh with this 8 noded continuous brick element on the active area. Then you apply the potential difference. So on that active area, basically, you are applying the voltage. So it will try to go back. So if you see, I can show you, it is at 0 kilovolt. When you apply, it will try to go back little bit again for 6 kilovolt. So you can see we can apply the voltage up to 6 kilovolt. After that, our solution is not going to give because it will not converge. But it's a very high voltage. You will get the actuation. Okay. Now you can see a very good match. Not a very good match, I'm saying. It's a qualitative, not a quantitatively match. The trends are basically the same. If you see, we are getting the same trends here, okay, as we are getting experimentally. So that always give us the confidence that at least we are going in the right direction. Definitely source of discrepancy is there. Can you identify what are the source of discrepancy? Why experimental we are carrying out on VHB tape and FEM we have developed? 8 noded brick element give the exact result, exact match. But when we are making the comparison of the final attained equilibrium angle, it will have some discrepancy. Can you identify some reasons? Sorry? External environmental condition is there. But if you see in the model carefully, have I considered the viscoelastic effect here? I have not considered viscoelastic effect here. It's a simple model, hyperelastic. But our VHB tape that we are using, I have already told you, it exhibits strong viscoelastic behavior. So that angle that is obtained by actual experimental, it have the viscoelastic property. But in the model, we have neglected the viscoelastic behavior. That is one thing. Second thing is, if you conduct multiple experiments, so this symbol basically represent, it's not a single experiment, it's a set of 3 to 5 experiments we have conducted for a particular level of applied voltage. For this configuration is obtained for 3 or 5 different angle, and that center one is the average value of that. This is the upper limit, this is the lower limit. So experimentally we are also having the source of variation is being there. So what are the things in order to avoid this source of discrepancy? First thing is, we have to incorporate viscoelastic behavior. That is one thing. Second thing is that we have to always consider that we have done already in here, we take the average value. So more or less the experimental average value will be the exact value, closer to the exact value. If you have conducted 10 experiments, so if you take an average, so at least you are in some range of towards the exact value. That is the other thing. Third thing is, try to use some automation in the fabrication of the DMS actuator. How? Spray up technique. That is other thing. Because most of the cases, if you see, the error creep in because of the non-uniform distribution of the electrode. Third thing is, in this formulation, we have neglected the mass of the electrode. In actually, when you put the carbon grease over that, mass of the electrode has to be taken into account. So if you are not taking, some variation will be there. So these are some source of variation, and the way to overcome that I have already tell you. If you incorporate viscoelasticity in finite element model, you get more accurate result. So already one of our colleague has done this thing. He has done all the finite element analysis with, like, he know that Professor Atul Kumar Sharma has done that. So he has developed a finite element model during his PhD, the first model for incorporating viscoelastic behavior in dielectric elastomer membrane. Also anisotropic model, finite element, complete finite element model. Okay. So you can go through that. If we integrate that model here, we will get a very good result, but it's not that much easy. You are defining everything UMAT and user defined element in Abacus software. Incorporating this effect is a very, very tedious process. Your tangent modulus that you are having, it is going to be a very, very huge equation for that. But still, if you, yesterday Prashant Saxena sir has told, two ways are there. Make some assumption, you will get at least good trend, make your life easy. If you use some complicated model, very, very difficult to solve, but if you are able to solve, you will get the exact result. So that same technique has to be followed here. Depends what you want. Most accurate result, then you have to define you have to remove all the source of ambiguity. But if you want some trends or something to match with the experimental key, okay, it is giving actually the trend, then you can incorporate the simple hyperelastic model. Getting my point? So any doubt till now? Neuron network, very, very important. This we have already discussed. So I says initially we have developed a thing that why we are considering some particular shape, rectangular. We can go for different shape of the electrode as well as the shape of the frame. So here, in this case, we can have the rectangular frame with rectangular electrode or with circular electrode or triangular electrode or any other shape you can suggest. These are most commercially available or commercially used shape that is easily we can implement. Because we have to fabricate ultimately also. Na? So if you take something different shape, it's very difficult to fabricate also. So judiciously take some different shape like triangle, circle, rectangle, square. They are easily to implement experimentally and in the finite element. So we have obtained that if we change the shape, you can see that there is some variation in the attained equilibrium angle and the final actuated angle. All this simulation is carried out by using this develop finite element model. Okay. Now the important thing, initial development is for simple case. We have taken to the advanced cases. We have already seen this experimentally. So finite element, it's very, very difficult. I'm telling you, it's look quite easy. When you develop all this thing, okay, in finite element, separate, you have to do the simulation part. So one simulation for solving electromechanical part, third simulation only, it takes 6 to 7 hours. Why? Because lakhs of mesh element will be there. I can show. In this configuration, if you see, it's for initial one, number of element is very huge. Okay. So it's not that much easy that you are thinking. Step 1, step 2 is easy. Define the geometry, material property, carried out the simple simulation, get the principal stress and incorporate in that one. In third step, it's a very, very tedious, and it's not also that much easy in Abacus. You have to link the parallel studio. Okay, in coding that I've shown you is you have to done in C language basically. So you have to get the knowledge of C, how to implement that. Then parallel studio basically connecting this Abacus with the constitutive model in the C Abacus, C formulation, C programming that we are doing. So 3 different things you have to couple together. So parallel studio basically coupling these 2 things. Okay. So these are the basic step for the evaluation of one of the case. First we pre-state separately, okay, obtain the principal stress condition. Then we are having the actual geometrical shape in which what we are doing, we implement this pre-stress condition to the membrane and attain the initial equilibrium configuration. And this initial equilibrium configuration, the third step, we have developed the user-defined element subroutine by which we implement the voltage to this active area of the membrane, then it will try to flap. So this is the entire methodology step by step. Initial, one simulation, provide the pre-stage, obtain the principal stresses, okay. That principal stress you provide to the membrane, fine. Membrane, and then obtain the initial configuration without voltage. And on that obtained initial configuration, apply the voltage to this particular active area. So what is happening when you apply it? It will flip like this, okay. So that is the basic methodology need to implement for carrying out a complete electromechanical response of dielectric elastomer based minimum energy structure, okay. So we have carried out very rigorously a lot of simulation without warping. We are trying to see whether in some of the cases whether without stiffener it works or not. So the same result we are getting when we are not implementing stiffener. So you see that is the major case where you always require the incorporation of stiffener. Huge warping. When it try to hold some object, already it's bent like this out of plane. It will not able to grip that object. So to avoid that, stiffener has been implemented, and you can see how effectively it will now. For example, if voltage is being increased, it can initially hold the object, and voltage applied, it can release the object. So it can basically play a very, very important role, but incorporation of stiffener. Fine. Any question till now? So you can see for different pre-stage, as anticipated, larger the pre-stage, larger the strain energy of the membrane, it will try to bend the structure more. So that is being obtained also with the simulation. So larger number of stages. So lambda is basically here lambda 1 equal to lambda 2 equal to 2 biaxial pre-stage. So it's very, very large. So you see for a higher pre-stage, our structure is going to curve, and that we have obtained experimentally also. If we go back, I can show you the experimental part. This is, you can see. For higher pre-stage, that is biaxial, lambda 1, lambda 2, 2, so it will curl like this. So simulation wise also, you can see it will curl. So it shows that we are basically going in the right direction. Source of discrepancy is there still, I am not saying, because FEM is also like it's a numerical tool, it's an approximate solution. It will always give you an approximate solution, okay. Now when the voltage is applied for this particular case, it will try to open up, okay. So you can see with the help of this finite element like GIF, how it is basically working. Initially, the pre-stage, because of the pre-stage, it will try to go like this, and when the voltage is applied, it will try to flip, okay. Then we have extended our work to flapping wing. When no stiffener are used, warping, stiffener are used, complete warping is elevated. When stiffener are oriented at a certain angle, bending and twisting modes are obtained. So everything that we have defined experimentally, we have obtained with the help of finite element. So parallelly, I have shown you the experimental view also, okay. Now the important thing is the angle orientation that we have play a very, very important role. So what are the options? We can have the stiffener at a certain orientation. Any angle we can take, 37.5, 42.5, whatever we want. But we have taken the standard angle, 30, 45, 60, 90 and 0. So 90 is there, 0 is not there. 90 means it is stiffener at right angle to the frame. Okay. So you can clearly observe that when we increase the pre-stretch of the flapping wing, our wings will be initially bend more because membrane energy is more, it will try to bend the structure more. Okay. Further, the frame bending stiffness play an important role. If it is going to be large, so definitely it is going to offer some resistance to the bending of the structure. Okay. That is one of the other case study. So here you can see that if we are having the different orientation of the stiffener, initially we are having only the bending mode. But for all the other cases along with the bending, it will try to have twisting also. So when we actuate, it will show like this, bending and twisting. Okay. So that is the role of the stiffener, avoid warping. Okay. By changing the consecutive distance between the stiffener, you can tune the attained shape, tune attained angle, and by providing at a certain orientation, you can obtain bending and twisting modes. Fine. So this is the final simulation in which initially this is the structure is being obtained when you have provided the pre-stitch, and when you apply the voltage, it will try to flip like this. So this is the structure that is obtained at different amount of the supplied voltage. So I hope the finite element simulation is clear. It's very, very tedious exercise. I will share my all the abacus file with you. Okay, you can go through. But one of my suggestion that I have done because of my learning, go for the console software, because platform is same, steps are same, process are same. But this is initially is very good. The reason is I have get expertise in all these things. It look very easy to me now because I have everything ready with me. But if you go and you start developing the things, UEL, UMAT, get वो first जो parallel studio you will try to link na, it will take around very huge time. It is some you have to download some particular version of the abacus and particular version of the Intel Parallel Studio and C programming. Then they will get linked together. If any of the version that is not compatible with the other will not get installed, even not get linked. So in installation it will take some time. Then understanding of the things, C programming, you have to go and constitutive model remain the same that we have, okay, but you have to implement in the syntax of the C program. Then you have to define the geometrical shape, everything in some of the software, import into the abacus. Okay, for the simple shape is already being imported. It being developed in the directly in the abacus, but complicated shapes are directly imported. So it's a time consuming. COMSOL, direct electromechanical coupling is element is there. UEL, you need not to define anything. That is one thing. So direct you can go with the COMSOL if you are basically starting in an initial phase. But for my student, I always prefer to go with the abacus. The reason is I am having the expertise. If they got stuck somewhere, I can able to help them. Even also I can help. But the thing is we are not in the in-person contact with each other. Okay. Okay. So this is I want to cover yesterday, but due to some reason we have not able to cover. Okay. So any question, online audience, if you have any question, you can free to ask. So any question from your side? Slide share करनी है? You want my slides? I can give, no problem. So now the today's topic of discussion is advanced topic and case study in soft active material. So I am trying to show you, Dr. Prashant Saxena will discuss some instability today, the wrinkling one. He has started yesterday, okay? And he is going to show you the techniques like artificial intelligence, how we are implementing in soft active material. So that is then basically the advanced studies or advanced topic nowadays. I have already told you it's being very trending. So I will start with some instability modes and then I will take you to the artificial intelligence based techniques, okay? So here you have one of the things that I have already discussed from the beginning, that this dielectric membrane has some challenges. I am never say if it's a disadvantage, I am saying it's a challenges. If you are able to handle that challenge, you can use them effectively for different applications, okay? So the important challenge is morphological and operational instability. Now what is happening when you are supplying the voltage or potential difference to the membrane? So initially what is happening, it will compress the membrane in the thickness direction, but as you keep on increasing the voltage, it will compress more. So a stage will come when the thinning of the membrane will take place, extreme thinning, and at that point what is happening, the breakdown of the membrane will take place. So you can see at this figure, so as you keep on increasing the voltage, the membrane electrical breakdown will take place at a particular threshold voltage. So that voltage is called as critical voltage or critical electric field that you supply, in which the abrupt thinning of the membrane will take place and which ultimately lead to the failure of the device. So make my word clear, failure. So there is a difference between damage and the failure. So you know the difference between damage and the failure? So what is damage and what is failure? Any one of you? In failure you can improve. How? If your device get fail, how you improve?
Damage we can bear, but failure we can't bear.
Yes. So damage is like that. I give a simple example. If you are having a composite, a fiber is there, a matrix is there. For example, if your fibers get failed, some of the fibers get failed, so it is called as damage of the composite structure. Still in that case, matrix can take some load. It can perform its function. But in the failure, your device is never going to perform its function. So यहाँ breakdown हो गया तो हो गया. It's a failure. It's not a damage. So damage in which your component or device can still perform its function up to some time, up to certain time. ऐसा नहीं कि वो continuously करता रहेगा, no. But in the failure, the device is not going to perform its function for which it is being designed. So that is the failure. So here I am talking about the failure. So it is a electrical breakdown, that is basically called a failure of the dielectric membrane. So that instability because of which electrical breakdown occur, and it is basically it is commonly referred as pull-in instability. Why pull-in? Because what is happening, you are trying to basically pull in the other direction and basically compressing in the thickness direction. So because of the application of the voltage, a electrical breakdown is occur and is commonly called as pull-in instability. Very, very common modes of failure in dielectric membrane. So lot of ways you can improve this pull-in instability. So the thing is, first is how you can improve the pull-in stability. I have already told you, by incorporating some anisotropic behavior. It can delay the onset of the pull-in stability. Okay, people are doing, they are basically combining this dielectric membrane with, during their fabrication with some ingredients, some chemical they are incorporating, that delay the onset of pull-in stability. So that is one mode of failure, pull-in instability. Second one is the wrinkle. Dr. Prashant Saxena started discussing about the wrinkling instability. So you can see this is a type of wrinkle that will be developed. So usually people say it's an instability. When the wrinkles come, the people say it's a type of instability in dielectric membrane. In the literature, you also find the word wrinkling instability. Most of the cases, they are using this word wrinkling instability. But as he has told that this instability we can harness them, or we can exploit them for the different application. That's what we are doing also here. So I have a project of the DST in which we are trying to harness this wrinkle behavior for the development of different applications. Smart window application, surface patterning, for like grating, we can use them, this wrinkle. So our target is to develop the stable reversible wrinkle. So stable reversible, mark my word, stable and reversible. Reversible means when voltage you remove, it will come back to its original configuration. Stable means they are basically not an unstable one. For example, you are getting that wrinkle at a particular part and you are not getting. So you are getting a uniform stable wrinkle throughout the active area. That is one more thing. So you can see we have developed a methodology. In order to measure the wrinkles, there is an analysis called as tau domain analysis. I will explain what is this tau domain analysis. So for the measurement of the wrinkling behavior, there is a mathematical technique that is called as tau domain analysis. Okay. So first try to understand we understand what is pull-in stability, what is wrinkling. So when basically wrinkling is, we are having a dielectric membrane. When you apply the in-plane compression, you are applying the compressive force, the wrinkle will be developed. So wrinkling is basically out of plane deformation of the membrane to relax the in-plane compressive stress. What is happening? You are providing in-plane compressive stress, your out of plane deformation in the form of the wrinkles will be occurring. So wrinkling is a phenomena that is representing the out of plane deformation of the membrane to relax the in-plane compressive stresses that is being developed. So वो जो in-plane compressive stress develop हो रहे हैं, that can be mechanically or because of the application of the electric voltage. Okay. So I hope you understand what is wrinkling. Now see, for example, if we are having a dielectric membrane, we pre-stretch that membrane in one particular direction. You can see, you can visualize from here. We are having our stretching mechanism. I have shown you yesterday. So we have pre-stretch in one particular direction, uniaxial pre-stretching of the membrane. Okay, and then what we are doing, we are make some PLA based rigid frame. So that rigid frame we are having the inset of two. One frame we put at the top of the pre-stretch membrane, and one we are putting at the bottom of the membrane. Simple. It's a hollow frame made up of PLA material with some thickness, but it is rigid now. Okay, so at the top, at the bottom, you are having that PLA based frame. You put it over that. Now you at the center portion you put with the help of a carbon grease the electrode you try to develop. Okay, Now this membrane is basically pre-stretched in this particular direction. So after removing from the razor blade, it will look like this. This membrane inside, it's a pre-stretched membrane, but it is not aligned to come back and going like this, because we have fixed the boundary by providing a rigid PLA based frame. So it will look like this. Okay. So now you apply the potential difference. Now see the fact, it is pre-stretched in one particular direction, very large amount, say 4, and in other direction it is not pre-stretched. Definitely the stresses will be developed in this direction and in the other direction also, but in the other direction it's very, very less. When you apply the electric voltage, what is happening? The stress in the other direction where you have not provided the pre-stretch, it vanishes first. Okay, when you apply the potential difference, so what is happening? The stretch in the other direction will vanish first. And because of the application of the voltage, what is happening? What is happening? Aerial expansion, in plane compression. So that basic phenomena that you are using, you implement here when you keep on increasing the voltage. So what is happening? Initially when the voltage is very low, it's simple, nothing. You are having a simple your structure with you, in which pre-stretched D membrane is there in between. Okay. As you keep on increasing the voltage, after certain level of the applied voltage, the wrinkle will start to form, and where? In the direction parallel to the direction of the larger pre-stretch. So where you provide lot of pre-stretch, that is the same phenomena. You provide this. So here you are initially not providing anything, but you are providing in-plane compressive force. So in the direction of the larger pre-stretch, for example, if you have provided pre-stretch in x1 direction, so parallel to that x1, wrinkles will develop. Or in this case, if you are having x1 here, so wrinkle will develop like this. So here in x1 direction we have pre-stretch. So what is ultimately physics behind it? In the direction of the larger pre-stretch, when you applied the voltage, stress will still remain, but in the other direction, because of the application of the voltage, stress vanishes first, because there is no pre-stretch there. So ultimately what is happening? We are trying to provide the in-plane compressive force, and wrinkle will start develop in the direction of the larger pre-stretch. Now the thing is, if you see at this particular voltage, you can clearly visualize the wrinkles begin to form and wrinkle will be there. This is a stable wrinkle. But after certain increase, 0.4535, this is electric field. Increase in that, your membrane will get failure. So this failure is basically what? It is the pull instability, the electrical breakdown in the wrinkle configuration. So you see in the wrinkle configuration, the electrical breakdown will take place. But as an engineer, I can say for this level of the voltage, our structure is safe and it will show stable wrinkling behavior. So, and for this, you see lambda 1 is 4, lambda 2 is 1. So larger pre-stretch in one direction, no pre-stretch in the other direction. So what are the varying parameter here? Pre-stretch. If I change the pre-stretch, for example, lambda 3 is 2 or 2 something or 2 and 2. So what is happening? The second case, the stress in the other direction is not vanishing. So no wrinkle will be developed. So it always remain in the taut state. Taut state means tensile configuration. Both lambda 1 and lambda 2 will remain positive. And it will give a stresses that value. So no in-plane compressive stress will be developing. No wrinkle will be developing. That you have seen the energy relaxation theorem that Professor Prashant Saxena explained. Either if one of them will be negative, lambda 1 or lambda 2 means compressive, the wrinkle will be forming. You're getting my point? So I can show you visualization of that. More clear picture. At low electric field, no wrinkle. You can see from here, or more clear interpretation. At this voltage, no wrinkle. You increase the voltage, wrinkle will form. Okay? At higher voltage, more clear visible wrinkles is formed. For up to this voltage, it is stable and reversible. Now you increase little bit, 5750, this is the value. You see now the failure will take place in the wrinkled configuration, electrical breakdown. Have you seen? So, as an engineer, I can say that for particular level of the pre-stretch, I know the value of the electrical voltage for which I will get the stable wrinkle. So, I develop a device, I pre-stretch a membrane and put it there, and with the help of a circuit, electric circuit, I supply a particular voltage, but up to which extent it will not get failed. As I keep on switching on the voltage, wrinkle form. As I switch off the voltage, wrinkle will go back. So if you see, it's a reversible in nature. That is the very, very advantageous effect of this stable wrinkle. So I hope you are getting. So application wise, I have already discussed. We have already developed, I think Divyansh has worked on this, Akhilendra Singh you have worked with. So we have developed we have put the patterned electrode. I want the wrinkle at this particular location. In center I don't want, at this location I want. Then again I don't want. So we can play with these wrinkles. So we are the one who will define where we want the occurrence of the wrinkle and when to stop that wrinkle. So basically we can tune this stable wrinkling pattern in dielectric memory. That is one thing. Now how we can basically mathematically define this wrinkle behavior. So there is a tau state phenomena. So that represents the two configuration. Yeah, please.
Like in your case, sir, you have completely that active area is completely hold the.
In this case, it's completely active.
But अगर ये at border जो आप एक डायलेक्ट से फिक्स किए हैं, अगर उसके active area को अगर reduce करते हैं, like वो completely filled नहीं रहेगा. In that case, that particular wrinkle is not found means in a.
That is the thing. So that active area is very, very important. So the applied voltage will have in the active area it is going to affect that. Na? You're getting my point? So uniform यहाँ पे we have the uniform distribution of the electrode. So in the other case, for example, if we are just putting the active area at the center of this and we are applying the voltage. So when you are applying the voltage, definitely the membrane is completely pre-stretched, but you are applying the voltage, in that active area you are going to see the effect of the electric voltage. You're getting my point? So that's what I'm telling. If you are having not like uniform distribution of the patterned electrode you are using. So that we have developed, actually that video is still missing with us. For example, I put electrode here, no electrode here, then again here, then at the corner. When you apply the electric voltage and make the connection, so you will see or visualize the wrinkle at the location of the active area. You're getting my point? So that is the thing. In this way I am telling you we can play with this wrinkle. Where I want, where I don't want. So the second application is smart window application that I am discussing. So this is the way we have the only parallel wrinkle. So there is a technique by which if we put something like that, obstruction or some stiffening element in between fibers, and we are defining the occurrence of the wrinkle in that pattern. For example, in some Prashant section has told like we are having the flow of the fluid like this. So we define that we want in such a way that it will flash my name. The wrinkle will flash my name. So for that you have to constrain some areas, provide the active areas like this. Okay. So after providing some constraint to that, your wrinkle will be of particular shape that you want. So for example, if I open the voltage, it flash my name. I switch off the voltage, it will vanish. And the advancement is that in that basically case, if you provide some lightning thing, along with the electric voltage on, some light will also go through that wrinkle area. So your name will be basically coming at the front with the lightning effect. That is the concept of smart window application. Okay. I hope you are getting. Now try to understand how mathematically we can formulate this. That is very, very important. So for modeling this, there is a concept called tau domain. So tau domain is what? If you see this region that we are developing is called as tau domain, and it is nothing, it is the in-plane principal stretch. So lambda 1, lambda 2 are the in-plane principal stretch. So on this axis we are having stretch lambda 1, we are having stretch lambda 2. So the tau domain is basically representing the in-plane principal stretch when both of them are positive. When both of them positive, in this configuration it is called as tensile configuration. If one of them is negative, for example, if one of them is compressive and another is tensile, so definitely where will be, it will be compressive. So for example, if it is compressive in this direction, so the wrinkles are forming in the direction parallel to the tensile one. So that region is called as wrinkled configuration. There is a tensile configuration when both in-plane principal stretch are positive or stresses are tensile. When one of the stresses is compressive, either this one or this one, then it is called as wrinkled configuration. Getting my point? Yesterday, he has started with the energy relaxation part. There you have seen lambda 1, lambda 2. Okay. So if one of them will be a negative, so that wrinkle will develop.
Left side वाला region T11 negative का है और right वाला region
Uska negative. So that is showing that. So if one of them will be negative, so the wrinkle will start developing. So you understand the tau domain, how it is it is nothing. It is the representation of in-plane principal stretch of the soft active material, lambda 1, lambda 2. So if one of both are positive, it is called as tensile configuration or tau domain region. So this region is called as tensile, both are positive, you see. So it is called as tau domain region or tensile configuration. If one of them is negative, it's called as wrinkled configuration. So depending which one is negative, your direction of the wrinkle will be defining based on that. Mathematically, I have one paper to show you. So this is our paper. So what we are doing, we use the same concept. If we incorporate some anisotropy in the dielectric membrane, however this tensile configuration, tau domain, wrinkle behavior will going to be affected with that. So I will just give a glimpse of that paper, you understand it. So this is our membrane is now electromagnetoactive membrane. So already we have seen that nowadays the actuation mechanism can be tuned by implementing electric and magnetic field together. So we are having one class electroactive polymer, magnetoactive polymer. Nowadays electromagnetoactive polymer is widely used. So physically, like, still people are developing this type of material. How? For example, in the dielectric material, if you incorporate some magnetic particle, you are getting my point? During fabrication, if you are having a dielectric elastomer membrane, if you integrate it with some magnetic particle, it will behave like an electromagnetoactive particle, membrane basically. So you can have the controllability by using two actuation mechanism, electric and magnetic. Okay. So in this we obtain again the same concept, transversely isotropic, we put the fibers. Okay. So this is already we know that invariants I1, I2, I3. So now there is certain invariant come into picture because of the applied electric field, magnetic field and the fibers. So we are giving the fibers, okay. And that fiber you can see it is initially at the, like it is initially horizontal, but it can be also at a certain orientation. So in this paper we have tried to analyze the effect of fiber reinforcement strength, Xi1, and fiber orientation. If we orient the fiber at a certain angle, how it is going to affect our tau to domain behavior. Okay. So we define this basically already existing one. So इस पे आपको इतना work करने की जरूरत नहीं है. Just go through it physically. What I1 is representing, trace of B. What is mean that? What is I2? What is I3? You have to go through this in a detail. But expression you need not to derive it again and again. Okay. Now this we have already seen that this is a total stress tensor T. Minus P, P is a Lagrangian multiplier, hydrostatic pressure that we are considering. So different terms, Xi1, Xi2, it is a strain energy part. Psi1 is obtained by, basically how you can obtain Psi1? By, if you have this expression, del psi, the total strain energy. So total strain energies can be by using different hyperelastic models. So if you integrate by del I1, you will get Psi1. If you differentiate. If you differentiate with respect to second invariant, you will get Psi2. So in this expression, so this is the expression for electromagnetoelastic membrane. So agar electric magnetic nahi hoga, this term will get vanish. B, this one, H1. No fiber, this term will get vanish. No electric, this term will get vanish. So addition hota gaya terms ka because of the incorporation of different actuation. Okay. So this is the strain energy. So from where it comes again, augmented energy in which initialized is in the Neo-Hawkian model. This term is for basically mechanical part, Neo-Hawkian part. This is an electric part, this is magnetic part. Epsilon naught and Xi naught is electric permittivity and Xi naught is magnetic permeability. Okay. Then we are having this transversely isotropic, we have seen mu by 2 Xi into particular this direction where you are basically incorporating the fiber. That term square will come. But an additional higher order term will also come here. Why? Because we are considering 2 Xi1 here. So again, this all are well developed derivation. You just go through that, need not to derive it again. I am telling you. So अब आप I1, I2, I3 तो जाके derive नहीं करने बैठ जाएंगे. Because it's already well defined in the literature. So you are judiciously, you have to think which parameter you can directly taken. ओके आप फॉर एग्जांपल आइंस्टीन ने कोई थ्योरी प्रूफ करी, आप उसको दोबारा प्रूफ करने तो नहीं बैठेंगे, यू कैन डायरेक्टली यूज दैट फॉर्मूला, सेम कंसेप्ट, बट यू हैव टू अंडरस्टैंड द फिजिक्स बिहाइंड इट. This component is coming because of the fiber. This is coming because of the magnetic field. This is coming because of the electric field. Okay. So by incorporating this strain energy part, you can obtain the stress component T11, T22, T33. ये एक्सरसाइज डॉक्टर दीपक कुमार सर ने भी कराई है सेम, बट फॉर सिंपल डाइलेक्ट्रिक मेमोरी. ठीक है. सो इफ यू वांट टू एलिवेट दिस T33, you want to find the value of this P, so you says that our boundary is stress free. So put T33 equal to 0, you find the value of P, put it back in T11, T22. So you will have the expression of, by putting the value of Lagrangian multiplier, you have the expression of T11, T22. Okay. So what is happening? What is the concept we are applying? If we are considering the concept of uniaxial tension, uniaxial elongation, so what we expect that the stress in the other direction will vanish first. So that condition, after getting T11, T22, just put one of them. So this is normalization we have done, nothing big. So here in this case, when you put one of the stress to be 0, you get this expression. So T11, you have already the value, T11, T22. So if you are applying a uniaxial tension in one of the direction, the stress in the other direction, we are assuming it will vanish. Okay. So keep that value to be 0. So you get an equation. So that equation is in terms of the lambda 1, lambda 2. So that is the equation of your tau domain basically, this equation. So when you try to solve this equation, okay, in the MATLAB, your this type of graph will be plotted. This is called as tau domain graph. Definitely it will have an electrical term, magnetic term, okay. So one thing I try to explain here, I can show. Here magnetic field is 0, okay. Epsilon 1 is 0, means no anisotropy. Alpha is 0, means orientation is horizontal. So this is for the validation part, because we are comparing with the standard dielectric membrane. So isotropic dielectric membrane we are comparing. So magnetic field is 0, because in dielectric only electric field is there. Anisotropy is not there because we are considering isotropic membrane, okay. So you can see what is happening. At particular level of the applied electric voltage, your tau domain will be there. As you keep on increasing this voltage, so it will shrink down. And at a particular value, you can see it will reduce to a single point. So that single point means it is representing that now the breakdown of the membrane will take place. So if you keep on increasing the electric voltage, it's of no application. So that indicates the occurrence of pull-in instability in the smart material. You're getting my point? So how the tau domain is used to find out the pull-in instability of the dielectric material. Now if we are considering about the wrinkle region, so basically if we want to define a region wrinkle free, or we are trying to develop a wrinkle free region, so this region basically is a region in which no wrinkle will occur. Why? Because we are having both the stresses to be positive, like we are having both the stresses to be positive, no compressive stress will be developed. So this region, if we want to define a region wrinkle free or wrinkle resistant region we want to define with the help of tau domain, this is that region. Outside this, there is a possibility that wrinkle will form. You are getting my point? So in this paper what we have done, after validation, we are trying to see the effect of the electric field on anisotropic. If we incorporate the anisotropic effect for zero orientation and the effect of the magnetic field, variation of the magnetic field parallelly, okay. And one good thing is you can see we change the strength of the reinforcement of the fiber. So what is happening here, when we change the strength of reinforcement of the fiber, our tau domain keep on expanding. So it shows that if we keep on increasing the strength of the reinforcement of the fiber, you are getting a bigger tau domain region, or you are getting a region where no wrinkles will be produced. So जितना बड़ा region होता जाएगा, उसके बाहर वाले region में you are getting the wrinkle, but inside that you are getting a safe zone as wrinkling instability नहीं आएगी. You are getting my point? Similarly, we have done for the orientation. We change the fiber orientation 0, 30, 45, 60, 90 तक ले गए. So you can see how it is going to govern your tau domain region. Tau domain, you understand what is tau domain? It is the in-plane principal stretches. It is the graph representing the in-plane principal stretch. When both are positive, it is called as tensile configuration. When one of them is negative, it is called as wrinkled configuration. Okay. So that is the concept of tau domain. Any doubt till now? Anything you want to ask? So we understand what is wrinkling, what is pull-in stability, how we can harness wrinkle, how we can mathematically model the tau region. Okay. Okay. So last topic, I will not make you that much bore. That is also a trending one. This is the paper that I have discussed with you. Okay. So this is the glimpse, effect of anisotropy, effect of electric field, magnetic field, anisotropy and fiber orientation. So this is the basic outcome of this paper. We have find out the effect of this parameter on tau domain of the electromagneto-active membrane. Okay. Now, very, very important that we have already discussed. We have also started working on this topic. As I told you that nowadays artificial intelligence based techniques are very, very important. Okay. So artificial neural network. I hope you have heard about ANN. There is a technique called ANN. There is another technique, lot of technique are physics integrated neural network is there. Different type of neural network has been developed. Okay. So what it is we are going to do, they take some data, train, it's like your mind. Neural means your mind, neural network. So if you have your mind with you, I says that, I give you particular thing that if I give you this, you will get this. I give you one data like this. Then I say, I give you this, you will get this. So what is happening in your mind? It will get trained. If you give me this data, this is your output. If you give this data, this is your output. So after particular, like from the particular data I am giving you continuously, your mind is get trained that if he give me this, I will give him this. You are getting my point? Ab simple example ले लो machine का. If you give something, some initial input you will give, he knows that the machine basically is being developed in such a way that it will give you some particular output. Similarly, what is happening? Your mind get trained. If you give him something, he will give you something out of it. So what is happening? This is machine learning technique also. So we define the data. We says I will give you this input and you give me this output. Initially we are defining the machine, or I will tell you, yeah, if I will give you this, you will give me this. So what is happening at the later stage? Your mind will get trained. So अब मैं नहीं बताऊंगा. If I will give you something else, you know based on your trained mind or trained neural network that I have to give this. बात समझ में आ रही? So this is the basic concept. If you see here, in finite element simulation, I have told you it is a very, very rigorous and tedious process. One simulation takes 6 to 7 hours for getting one initial equilibrium angle. And one experiment, I am telling you, since this acrylic elastomer VHB is strong viscoelastic behavior, after pre-stretching, we have to keep it for 24 hours for stress relaxation. आप directly उसमें अगर if you put frame over that and obtain the equilibrium configuration, after some 1 or 2 days you see your angle what you are getting will get changed. So you are not getting the accurate result. So experimentally you are carrying out 24 hour आप उसको रख दीजिए, then you fabricate all this thing, you put it, you cut it, you apply the voltage. So for one equilibrium configuration it will take 25 to 30 hours. And one simulation part it will take 5 to 6 hours. If it take 5 to 6 hours when you have everything ready with you, all the principal stress data that you need to put for the membrane, all the developed code for applying the electromechanical coupling, that it will take 6 hours. How efficient, बहुत efficient आपका computer होगा, it will take 3 to 4 hours. Getting my point? So what is happening? So we think that why we need to conduct experiment again and again. I conduct experiment for some amount of pre-stretch, some amount of frame bending stiffness, and I obtain the data. Already I have done that thing. Why my student again need to carry that thing? But if I says him, I conduct an experiment for 2 pre-stretch, for this particular frame bending stiffness, I obtain this angle. Experimentally. Then I says, I conduct 3 or 4 experiments. I have already told you I have got 3 or 4 experiments I have carried out. Then I says to him, can I get the answer if I having the pre-stretch of 3 and frame bending stiffness of this, what is the attained equilibrium angle? You are getting my point? So that thing that problem, he has need not to conduct again and again the experiment, again and again not to solve with the finite element simulation. So he has to utilize effectively this techniques called artificial neural network. So it's like this. This paper basically we are trying to replicate and try to find the different result with the different parameter that we have not done experimentally in finite element. So we have developed the forearm gripper and the flapping wing. We have some finite element results, some experimental result with us. Okay. This is the basic architecture of the neural network. So you have to give input. Okay. You give input. There are some hidden layer in which you are having the neural network. So it will get based on your input, it will take, okay. Then you want output layer in which you define what output you want. So based on this neural network, you continuously supply the input and output, provide them, so it will train itself. So number of neuron is going to change inside it. So that is the basic architecture, you understand? Now the thing is, for example, if you are providing certain set of data, so on the neuron, if you are selecting the different neuron, so it will give weight to the particular data. For example, if you are supplying 3 input parameter, okay, then weight you have to define. You are saying that this is a very important one, or you give equal weightage. I am supplying what is my input? Pre-stretch, frame bending stiffness, electrical voltage, anisotropy parameter, fiber orientation, stiffener spacing. These are input. I have to define. What are the output? Attained equilibrium angle, final bending angle, actuation stroke, actuation range. This is going to be output. You're getting my point? So what it does, the neural network will train itself based on the number of neuron and the weightage that you are giving to the parameter. Okay. This is basic architecture. So I will discuss with you about this flapping wing actuator. This is the case. We have already obtained the result I have shown you for the different fiber orientation, spacing between the consecutive stiffeners, okay, different pre-stretch and different frame bending stiffness. So in this case, you have to judiciously define 3 processes. Keep some data for the testing, okay, keep some data for the validation, and keep some data for the training. Training you have to give 80% of the data. Most of the data is required for training. For the validation, you can keep the experimental part. Because we are saying now experimental will be the exact one. Okay. So for training, we are going to use most of the data that we are having with us. For validation, we keep some data. For testing, we have to give some data. That is clear. So in the flapping wing, if you go back here, what are the input? You can clearly visualize from here. Pre-stretch of the membrane. Larger the pre-stretch, more will be the initial bending of the structure. Second parameter is the spacing between this consecutive stiffener. Okay, we have already seen that the spacing between the consecutive stiffener will have the effect on the attained initial configuration and final configuration. Third parameter is what? Orientation of the stiffener. Okay, and when you change the spacing between the stiffener, your number of stiffener will also get changed. Area to wahi hai. If you increase the spacing, the number of stiffener will reduce. If you keep the small spacing, number of stiffener will keep on increasing. So this is input. One of the input is also voltage. You have to give the input voltage. Na? When you are defining the actuated configuration, you have to define the voltage. So this is also your input. What is the output? The attained initial equilibrium angle or initial angle. Final angle when voltage is applied. And this gap, initial minus final. It is called as actuation stroke or actuation range. Clear हुआ? ये data, okay. So this is the input variables that I have already discussed with you. This is the initial configuration angle beta in basically in degree. If we are flapping wing, we are having bending angle as well as twisting angle. So in case of a flapping wing, our output is bending angle as well as twisting angle and the actuation range. Okay, so that is also going to be your output. So initially for this we have defined. So we are using this set of data that we have for the training purpose. 80% data we have supplied. Okay. How much? Keshav, you have any?
Yes, sir.
You have to say anything about this? So he is currently working on this topic. Okay. And since You see here, the orientation is 90 degree, 60, 45, 30. And we also have a data for 90, like it is pre-stretch is also varying here. Number of stiffener is changing, spacing between the stiffener is changing. So we have obtained the different data. Okay. Now the role of ANN will come. So before predicting that, you have to decide which number of the neuron it is predicting the right result. So once your model is being developed, then you say that we fix it. We fix that model and always ask for the different input, what will be the output. So that trained, that whatever you are getting, there is a R square term. Here it should be not R, it should be R square term. So R square term, you know, regression analysis, what is R square? What? Correlation coefficient. So if it is very, very close to the 1, means you are getting the accurate prediction, or you have trained the model in a accurate way. So the more closer the R square will be to 0.99995, sorry, here R will be showing, it will be closer to 0.9995, means it is nearly close to 1. So your model is trained well. So ये अभी मैं direct दिखा रहा हूँ आपको. Lot of, after selecting lot of models, we will get this. किसी में 0.95 आ रहा था, 0.96 आ रहा था. तो final one I am showing you, the best trained one we are getting here. So after fixing that, we are saying that yes, this model is fixed, because now it is predicting the accurate result that we want. So this is the result. So we are considering with the applied voltage, the bending angle. So the FEM result, only the dotted one are the FEM result, and the other results are we are predicting by using this ANN. So हमने इतना ही set of experiment conduct, finite element carry out किया. उसके बाद if we want for the different parameters, all the other you are seeing, we have predicted by using ANN. He has not to conduct the finite element superposition again for 3 pre-stretch, for different voltage level, or in between. Orientation fiber, मैं बोल रहा हूँ, stiffener orientation is 37.5. So he is not going to manufacture it experimentally, do the finite element, put the orientation at 37.5. He already have a trained ANN network model which can directly predict. He give the input, this is the pre-stretch, this is the spacing, this is the orientation, output angle he will get directly. So this is the result you can see. By using this much of data, we can predict the other, for the other input parameter, what will be the output. Similarly, in this case, for the different pre-stretch, this is for voltage, the bending angle. So you see, initially we have the data for, if you go back and you can see, we have data for 0, 2, 4, 6. For pre-stretch 1.25, 1.5, 1.75, 2. That's it. But now, lot of, for different pre-stretch, for different applied voltage. Here you can see the different pre-stretch, different voltage. After training, you can predict it. So what is the advantage here? It will be, you can get a clear glimpse here. What is the advantage? So we are having this. First, let's try to see experimentally how we have done. We fabricate this, PET frame, cut all the dimension, okay. Then basically we assembled it on a pre-stretch membrane. So this entire process, fixing, if you are quite efficient operator, then it will take 1 to 2 hours. Very less time I am telling you, it will take 3 to 4 hours. If you are efficient person, let's say you take 1 to 2 hours for all this thing. Cutting of the frame, pre-stretching of the membrane, fixing the frame to the membrane, putting the stiffener, everything. But that all thing will be possible after the 24-hour stress relaxation of the membrane. So 24 hours this and 2 hours this. This is minimum I am taking. So how much time for getting a one equilibrium configuration? 25 to 26 hours. And that if you, some source of error will creep in, your entire structure will get fail. So source of error भी आ सकता है उसमें, ठीक है? That is one thing. Finite element, pre-stretch the membrane by applying the displacement condition, obtain the initial stresses. One simulation you have to carry it out. Then you have to define all this configuration complicated in FEM. Put the stiffeners, define the material for all the component, assemble them, supply this initial condition in the form of principal stresses, obtain the configuration. So this analysis, then apply the voltage to that active area. So this complete analysis, if you have everything ready with you, the coupled Intel Parallel Studio with Abacus, C language, everything coding with you, then it will take 5 to 6 hours. I am taking the least time that at least you have to require this much time. At most you can go to any point, any time. So at least 6 to 8 hours it will require. So all this process will give you a one single result. This complete process will give you a one single result for one equilibrium angle or equilibrium or final actuated angle. Now what you are doing, this finite element, for example, if somebody has already done or experiment somebody has already done, you take his data, like in my group I have already done, okay. So in the future I am not going to tell him you go and perform all the experiment, all the finite element simulation. He has data readily available, all are well published. He take that data, okay. He develop his ANN trained model, and in MATLAB it's very, very simple to use ANN. There is a separate toolbox. You can go, you have a lot of videos, just learn them, take a data, practice it, you can implement. Getting my point? So, but there is a concept. Behind this training, there are different algorithms. Bayesian approach is there. So you have to see which approach or which algorithm is being suitable for your data and which is giving the accurate result. So source of discrepancy ऐसे रह सकती है. The question should be, you are using finite element for training the model. Finite element itself is a approximate solution. So you are already having some error. Then you are training something out of it. Definitely you will again have the accumulation of that error. Somebody can ask simple question. It should come to your mind. So how then you can say your model is well trained? So the answer for is that you have conducted experiment. So first we are trying to match our FEM result. Yes, it is an approximate solution. We agree with that. But what we have done, we first carried out the mesh convergence analysis. Okay, sensitivity analysis. We perform. So we are trying to get as much as closer to our experimental result. And for example, if we incorporate all the required things like viscoelasticity, definitely we will have very much close corroboration with the experimental part. Then we use that for the train purpose. In the training itself, we make sure that our coefficient of relation should be nearly 1. So that again signifies that it is very, very going to predict the accurate result. So we are not giving the exact result, we understand, because it's all our numerical technique. It will an approximate solution. But the way we are trying to approach, at every stage, we are trying to minimize the error. So if you see, after training all this thing, you are having, it will take 1 to 2 hours. 1 to 2 hours bhi bahut zyada. If you have data, it will take only half an hour. I am taking 1 to 2 hours because if you want to gather some data, you put it in the tail and you're trying to fit the model. Which one is the best one for the different number of neuron, different algorithm, you test everything, then it will take 1 to 2 hours. Then you say that we are having our trained model in hand with us. So is it a single result? No. You're going to vary the input as much as you want. You are going to get the output in a single second. You're getting my point? So you can see the output is multiple. In this case, lot of efforts. In this case, lot of computational time, and output is single. Here, once after training, you can play with any number of input and output parameters. So that's why these techniques are very, very important.